Hey there! Have you ever wondered how to figure out the highest or lowest point of something? Imagine you're hiking up a mountain and you're trying to find the highest peak to take in the best view, or maybe you're planning the most efficient route to save time. In math, we do something very similar when we deal with maxima and minima. We look for the highest or lowest points of a function. Let me explain how this works and why it's important. First things first, let's talk about what maxima and minima actually are. Picture this, you're looking at the graph of a function and you notice that it goes up and then comes down like a little hill, or it goes down and then up like a valley. The highest point on a hill is called a maximum and the lowest point in a valley is called a minimum. These are the turning points of a function, and they tell us about where the function reaches its peak or its lowest value. Now, why do we care about these points? Well, maxima and minima are super useful in real-world problems. They help us in optimization tasks, finding the best possible outcome for a situation. For example, businesses use maxima to maximize profit and minimize cost. We'll get into some fun examples later. Now, let's dive a little deeper into how we actually find these maxima and minima. You might be asking, how do we know where these points are? Well, here's the deal. When we are trying to find a maximum or minimum, we look for critical points. Critical points are where the derivative of a function equals 0 or where the function is not differentiable. These are the places where the function changes direction. Either it stops going up and starts going down, or it stops going down and starts going up. To put it simply, we look for where the slope of the function is 0. In mathematical terms, if we have a function f of x, and we take its derivative f prime of x, we set it equal to 0 and solve. That's where we find the critical points. F prime of x equals 0 now. Not every critical point is a maximum or minimum, but they are the places to start our search. Okay, so now that we have the critical points, how do we know if they're maxima or minima? That's where the second derivative test comes in. Here's the key. If the second derivative f double prime of x is positive, the function is concave up, and we have a local minimum dot. If f double prime of x is negative, the function is concave down, and we have a local maximum dot. If f double prime of x equals 0, well, this test doesn't give us any info, and we need to use the first derivative test instead. Let's take a moment to look at how this works. If f of x equals x cubed minus 3x plus 3, we find the first derivative f prime of x equals 3x squared minus 3. Setting f prime of x equals 0 gives us x equals 1 and x equals negative 1. Now, we calculate the second derivative f double prime of x equals 6x. At x equals 1, f double prime of 1 equals 6, so this is a local minimum. At x equals negative 1, f double prime of negative 1 equals negative 6, so this is a local maximum. Let's apply what we've learned to solve a real problem. Suppose we have the function f of x equals x cubed minus 3x plus 3. To find the critical points, we take the derivative and set it equal to 0. We get f prime of x equals 3x squared minus 3. Setting this equal to 0, 3x squared minus 3 equals 0, which simplifies to x squared equals 1. So x equals 1 and x equals negative 1. Now, let's check these points using the second derivative test. We calculate the second derivative, f double prime of x equals 6x. At x equals 1, f double prime of 1 equals 6, so we have a local minimum. At x equals negative 1, f double prime of negative 1 equals negative 6. So we have a local maximum. Now we know that at x equals 1, the function has a local minimum, and at x equals negative 1, It has a local maximum. So, why does this matter in the real world? Well, maxima and minima are used everywhere. Let's take a business example. Imagine a company is trying to find the maximum profit it can make. The company models its profit function P of X, where X represents the number of units sold. By finding the maximum value of P of X, they can determine the best price to sell at in order to maximize profits. Similarly, engineers use minima to design systems that minimize energy consumption, and economists use extrema to model minimizing costs and maximizing output. In all these cases, derivatives help us identify the best possible outcome, whether we want to maximize or minimize something. To wrap it all up, maxima and minima are the mathematical tools that help us find the highest and lowest points of a function. We use derivatives to find critical points, and then we use the second derivative test to classify those points as maxima, minima, or points of inflection. Whether you're trying to maximize profit, minimize costs, or optimize any system, understanding how to find and classify extrema is key. In the next video, we'll explore some more advanced examples and applications of these concepts.